Good morning, everyone. I'm Jason. I'm one of the senior principal engineers at Atlassian working in search. And today I want to talk to you about taming your query latency and the journey that we went on in Atlassian. So first up, raise of hands. Who has had latency issues in OpenSearch before? Excellent. If people didn't put their hands up, I was going to tell everyone to leave, but excellent. We can go on with the talk. So Atlassian had problems as well, and we're going to be using Atlassian as the case study for how we improved our latency. So just a little bit of background of the area that we're looking at. This is the backend for Atlassian's Rovo search solution. So we're building relevant search with many ranking signals, many levels of rescoring to find the most relevant results. We're delivering a multi-tenanted index for cost efficiency reasons. We also need to enforce access controls. This is a big part of what we do, supporting the access controls of both first-party and third-party product data, ensuring that only people that should have access to documents can view them in the search results. And the solution was developed over over 5 years and bloated to quite a large query. 4,600 lines of query code of the search query was where we were at. And that was resulting in about 1.6 seconds response time, P90, for a large tenant. As you expect, this is not particularly great for people wanting to get the search results and find what they're looking for, get their job done. For everything that we did as part of the investigation, we were testing against 2.17 of OpenSearch. There are some changes since then in more recent versions like 3.0. I'll try and point out some of the changes that have been made, but largely this should be applicable to anyone. So where do we even start? There's a couple of things that are really important when doing performance investigations. I would be recommending that people try and get a data set a representative data set that they can use in a local environment. This actually becomes very important when iterating fast on ideas and being able to explore your problem space. Now, there's a couple of different options for getting such data, a representative data set. You might be lucky enough to have data in production that you can pull locally. That is not the case at Atlassian. We can't get we store customer data. We cannot pull that into our local environments. Dog fooding or staging environments might also be a good option that might be more representative of what a real world use case might be using. Synthetic data is also a great option these days, particularly when you're using a large language model to generate synthetic data. In our use case, we used our dog fooding environment, grabbed the data for that. It was a reasonable size data that we could use safely. It's also important to have a repeatable breakdown of your requests. You want to be able to run an experiment and know that you're not having a lot of things that are kind of other issues that are causing problems. So we force merge the index and disable caching. And we disabled caching because we wanted to understand because we were focusing on a P90, it's very common that in those scenarios, query cache is actually going to be cold in that scenario. So we wanted to make sure that we had a repeatable test for that. Lastly, you need a bag of ideas. The documentation is a great place to get such ideas from, of what possible things might be fixes to your problems. But you want to be able to have this set of ideas and explore the kind of latency areas of a query kind of in a breadth-first manner, kind of finding areas of improvement in different parts rather than focusing on individual parts. That means that you can get the overall improvement over time. In terms of tools that we used from open source, the phase took query parameter is really useful for giving you a bit of a breakdown within the request of where time is being spent and in what phases. The query and fetch is what we focused on. This gives us a breakdown of both the timing, the total timing of the query phase, which is the phase where you're actually performing the search and getting the document IDs, but also the fetch phase, where you do things like retrieve source, perform highlighting. If you're using the learning to rank model, this is where ranking signals feature logging occurs as well. Secondly, we use the profile API. On any search request, you can add profile equals true, and it will give you a breakdown of each step of your part of your search request, or every single query, and all of its child queries. The breakdown gives you information, low-level information about specific methods and the timings of those. Not only does it give you the timings, it also gives you the count. This can be really useful when comparing across environments, as well as getting a sense of if something is a more expensive part of the query because you're seeing a larger latency for a smaller number of invocations. So one of the first areas that we looked at for improvement was data placement. So we've talked about our multi-tenanted index, right? Well, what if we didn't use a multi-tenanted index? This is a big question. Were we building our solution on the wrong assumption? And what was the best experience that we could get with a single tenant on an index? So we did some assessments of whether we could move towards this index per tenant model. Unfortunately, there's a number of overheads that occur as part of an index. We observed from an empty index about 0.5 meg of overhead for each individual index. And if we tried to make use of a shard per tenant, so being smart with how we place data in, make sure that we aren't having tenants interfere with each other in a shard within an index, we noticed that there was about 100 kilobytes overhead. However, when we tried to pack these into an individual node, we ran into open file handle issues at about 3,500 shards on a node. Ultimately, this would require us to split our cluster up into many more clusters and increase our costs significantly. So this wasn't really an option to move towards this still. However, we wanted to know how close can we get to that ideal scenario of an index per tenant. So we ran a simple test. We have one tenant on an index, and then we duplicate it to 10 tenants on that index. And in this simple case, we observed about a 61% overhead that we're experiencing because of the multi-tenant tenants on our index. So where were the hotspots? What was causing there to be, given that we're not searching across things that across tenants, why were we experiencing this overhead? Well, there's two sets of fields that we were using in our document schema, and I'll categorize them into unique and common terms for a tenant. There were a lot of common terms that things like full text search that are going to be shared across tenant boundaries. But there are other things like states of enums of a document, booleans or auto increments. And what if you think about how this looks like in an index, in an inverted index, you have your dictionary of terms, and then for each term you have a postings list. And so these common terms had a mix of different tenants in that posting list that we needed to filter out, and that was what was adding the overhead. So what if we split those common terms? So we looked at adding some of our common fields that we used as part of our query, so things like status and access levels, and we prefixed them with the tenant ID. And we saw some reasonable improvements from doing this in a local environment. So we're now only at about 45% overhead in this scenario. So the next step was, well, what if we can co-locate the tenant's data together? Rather than when we're filtering and searching for documents for a tenant, having to skip over to different parts of the index, what if we moved them together in the index file? And that way, it can make use of things like file system caching and things like that so that it can get a more efficient read of the data. One of the tools that you have available for co-locating data is index sorting. So normally when you're writing things into an index, they roughly go into the order that you write them in. There's no necessary guarantee that happens, but that's roughly what ends up happening under the hood. Index sorting allows you to change that so that upon merge of, say, the segment files within an index, it will rearrange those documents so that they are in accordance to the index sorting. So in our case, we looked at adding the tenant ID as one of the sorts. And we managed to get the overhead down to about 20% in our scenario, which was a major improvement from where we started. Unfortunately for us, there was a limitation. Index sorting is not supported, doesn't support nested fields. If you've got nested fields in your schema, that's not currently supported right now. We're looking forward to being able to contribute this to the community and be able to make use of this one once we've done that. Next up, I wanted to talk about track total hits. Track total hits is a parameter that you can set on your request. When it's set to true, it returns the total count of all matches on that for your query. And when you set it to false, it doesn't return that. Pretty simple. But under the hood, it uses this to allow it to do some optimizations. When it's set to true, it has to track all the documents and find all the ones that are matching your query so that it can count them. When you set it to false, it's able to do some optimizations where it's maintaining what the minimum competitive score was and is able to skip over non-competitive documents, essentially skipping large portions of your index as you go. So we were expecting some major improvements from this. And we didn't get any. We were scratching our heads. We were like, what is going on? We know that the documentation is saying that we should see some good improvements. So what if we just simplify our query? Maybe there's something that's causing our query to have issues and not get make use of this optimization. So we just went to the bare, simplest query that we could think of, which is essentially our tenant filter and just a match, simple match. And in this scenario, we got a massive improvement, 51% reduction in our latency. So what is going on? Why is our normal query not seeing any improvement, but this simplified query is seeing a major improvement? Well, these fields that the track total hits roughly translates to these two values in the scoring mode for Lucene, where when you're using track total hits true, it uses the complete scoring mode, and when it's using the when it's false, it's using the top scores. Well, it turns out that we were using a function score as part of our query. It's the function score query type as part of our search request, and it currently is not capable of supporting this skipping over non-competitive documents. Fortunately for us, this was actually just turned out to be cruft in our code. We had moved away from using this, and it just was sitting in our query, not doing anything. It was just a wrapper around the inner query. So we removed that from the query, and we managed to see a 35% improvement on our actual query. Next up, I wanted to talk about Boolean queries. So Boolean queries, just in terms of a bit of terminology, when you're using must filter or must not, I consider this a conjunction query. And when you're using should, I consider this a disjunction query. I'll use these two. I'll be using these two terms moving forward. I just wanted to give you that explanation so that you understand what I'm talking about when I talk about conjunctions or disjunctions. So how does a conjunction query work under the hood? So in this case, we've got three parts of our query. We've got our permission filter, tenant filter, and our keyword match. First thing it does is it rearranges our queries based on a cost estimate. It it doesn't know how expensive a query is going to be, but it makes an assessment and guesses using heuristics which one is going to be the least expensive, and puts the least expensive one at the front, so we can hopefully optimize the query and get the result in the shortest amount of time. It then starts moving through that initial query that it's seen as the cheapest, and in that case, it found all of the filters matched. So it matched. It matched the query. When it goes to the next one, okay, that one didn't have any of the matching, so that one doesn't match. Next one, they all match, and so it it moves forward. That one didn't match, and that one didn't match. So in terms of conjunction performance, ideally you want to make sure you have a small overlap between the two. Even if the queries themselves, the subqueries, return a large set of documents, if there is a really slim overlap, you should still get a reasonable set of results back, because it will be able to kind of eliminate major portions of the index. The cost estimate is just an estimate, and so it can be wrong sometimes. So sometimes you're thinking that one part of your query is going to be preferred and should be the most efficient part, and it actually ends up that it isn't being used. Finally, there's a large amount of there's a bookkeeping that has to happen when there is a large overlap between the different queries. So even though if you have many large queries that have a large overlap between them, it'll end up having to do a lot of bookkeeping between those multiple subqueries. So, time for a case study. Tenant filter. So in our situation, we had our tenant filter looked roughly like this. We have a site ID that we're filtering on, and we also have a workspace ID. In Atlassian's data model, a workspace is actually always contained within a site. And so it turns out that everything that matches the workspace always matches the site. So one of those two queries was redundant, and we can just remove it. So we removed that, and we saw about a 14% improvement on latencies just from removing that one part of the query. Next up, I wanted to talk about disjunctions, how they function. So we have a similar situation where we have multiple subqueries, and a disjunction, the way that it works under the hood is it has to, it uses a priority queue in order to determine which subquery is kind of the one that's going to supply the next document. So in this case, the first one matches number one, and it reorganizes the priority queue. We've got number two matching. Now, when we get to one where it has overlap, it matches, but then it needs to do a bit of additional bookkeeping and make sure it advances each one of those subqueries past that until it reaches all of them that have passed that document in their iteration. And then finally, it advances to the final document. So similarly, ideally, there's minimal overlap. This means that it should mean that it can stride through one postings list at a time, and it doesn't have to do as much bookkeeping. How cheap a query is not prioritized as part of this. So you need to really consider all paths of your disjunction when considering this, and the subquery that might be chosen is essentially at the whims of what the priority queue decides is the most recent, the current subquery to iterate through. So case study for permissions, our permissions filter. So just a little background, our permission filter looks roughly like this. Is a very simplified view. We have some parts of our query where we want to identify kind of fast access, things that we know that the user definitely has access to. And so we add, they should either have maybe everyone has access, and then cases where we know they definitely have access. When we get to more complicated permissions, we fall back to a second one where we use a script to kind of confirm that they definitely have access to the document. And in the past, we saw some problems with our script, and so we added this prefix in front to eliminate documents that that definitely didn't have access. So essentially, this is a probably has access filter. So a couple of things to call out. Documentation clearly says that script queries are expensive and you shouldn't use them. It also says the same thing for prefix queries. You hopefully see where our problem was occurring. But then we looked at how we can improve the query. It turned out that this case of these really complex permissions where we needed to fall back to the scripts actually had a very small surface area that it hit. And so we changed away from using the prefix query to essentially identifying situations where we definitely need to fall back to this script and marking them ahead of time. So when we did this locally, we saw about a 7% increase in performance. However, when we did this against production, we saw a 19% improvement. So what's going on there? This is where it comes into, there's different types of expensive queries. I like to break them down into eager, expensive queries and lazily expensive queries. A script query is a lazily expensive query. It is expensive to compute, but only for each document that it has to consider. However, a prefix query is an eagerly expensive query. It has to do a bunch of upfront work to identify the terms that match that prefix. So it's looking through that dictionary and its inverted index and finding all the terms that match. And then after that, it's actually fairly efficient. And what we found was when we looked at the profile API results, we observed this when we looked at the build score method. We were seeing quite a high number for that, even though it was only invoked a small number of times. Finally, on Boolean queries, I just wanted to show you one cool trick we discovered as part of this. So one of the things that OpenSearch does internally is it rewrites your query to try and make it more efficient. And it's able to do, particularly there's a lot of optimizations that happen around Boolean queries. And particularly in cases where they have things like match-alls, and in certain cases it's able to simplify the query considerably. In our case, we were using the Learning to Rank plugin to do feature retrieval. And the way that you do that is you define one of these SLTR queries and you put it in a filter block as part of your query. In practice, this behaves like a match-all query. Essentially, it's really just a placeholder there in order for the plugin to function, but it's not really supposed to add any overhead. However, it does add a slight amount of overhead to it in that it still needs to do bookkeeping around processing every single document, even if that processing is incredibly cheap. However, if we wrap it in a Boolean with some smart uses of match-alls and shoulds, it actually completely eliminates as part of the code. So it turns something that is supposed to be essentially a no-op to literally not doing any work at all. We saved a couple in milliseconds using this trick. Next up, joins. So documentation clearly calls out joins are expensive. And this was a big area for us where we're saying we should try and eliminate our joins that we're doing. So the question that we immediately went to is, well, what if we denormalize the data? We have some parts of our query which we're storing on a parent document. And what if we just took that data that we're storing against that and denormalized it against the child documents, and then just perform the query against the child documents? So we coded that all up and we did our test. And we saw a decrease in performance, a 37% decrease. So we were very confused of what was going on. It was a bit disappointing, but what we looked into, how our query works is that we were using a disjunction query within our join, and it had many term queries within that join. what happens is that priority queue came back, and that bookkeeping that I was referring to before. Now, when doing, yes, it's true that a join is expensive because it adds an additional upfront cost to its query. It does one query up front and then queries performs the outer query using the results that it got from that. However, when moving that operation, which was a log n operation, that updating the maintenance on that priority queue, when we moved it to the outer query, what ended up happening is that ended up happening over a much larger number of documents, 2 to 3 orders of magnitude more documents. And as a result of that, it didn't actually, joins actually was actually helping us there, even though it was doing an upfront query. Now, your cases might not work like ours. Obviously, we've got a particular special scenario, and denormalizing may be an option for you. But it's worthwhile making sure that you experiment to actually prove that that it is improving things. Another area that we used was parallelism. So there's a couple of options for parallelism in OpenSearch. There's concurrent segment search. This is where within a particular shard of your index, OpenSearch is able to search the documents within that shard concurrently. It's able to break it into smaller pieces of work. Hybrid queries are a good way, and it's documented as a means to do both KNN and full text search and kind of merge those results together, and a good option for that. But it can also be used for parallelism. Finally, there's multi-search. It's kind of similar to hybrid search, except you have to bring your own merging algorithm. Hybrid search has those built in. Multi-search gives you more flexibility, but you have to figure out how to merge the results from those 2 different search requests. In Atlassian's case, we explored the kind of multi-search option rather than the hybrid search because we wanted more that we actually wanted that flexibility of how we merge the results together. So for concurrent segment search, when we tested this out, we tested an idealized scenario and we saw a significant improvement. About 50% improvement. Now this was idealized, so we kind of cheated a little bit in this example. This was essentially optimized for what would be the best result that concurrent segment search would give out of it. We would expect in a production environment to not be as good as this. Unfortunately, we did run into a couple of bugs that we had to patch into OpenSearch around concurrent segment search for our use cases, particularly for the Learning to Rank plugin. So we're hoping to be able to make use of this improvement as we can adopt that improvement from open source. The second thing that we did was we made use of multi-search to kind of split our recall. So I kind of talked about before where you can use things like multi-search or hybrid queries to search for KNN and full text search in parallel. But you can actually add more queries. There's no limit to that you have to restrict it to just that. And what we found was that there were some parts of our query that had that were quite expensive, and there were a lot of personalization signals that we could do in parallel to the rest of our query. And so we split that those parts up, so we had 3 different recall paths. When we did this, we saw about a 10% improvement in performance there. Now, I've gone through a bunch of ideas. We had a bunch more ideas. I'm just going to blast through these as quickly as possible that worked well for us. Copy to instead of multi-match, so you can copy the fields if you're searching across multiple fields into a single one and just search that. We saw about a 30% improvement when we did this. It does have relevance implications of doing this though. We were using the Learning to Rank plugin for feature retrieval. And we found that because the way that it functions is to use that inverted index to do these calculations, there's some types of features that are actually more expensive to compute using this method than simply just retrieving the fields that we're using for that feature and just computing them client-side. So we shifted some of our features across from the SLTR plugin to source retrieval, and we saw some improvements there. Finally, we did explore sharding our fields, so splitting them and then selecting a field based on the tenant that's querying, and this splits that posting list up for common terms further. Finally, we also converted our rankers across to using the Learning to Rank plugin. Now, the Learning to Rank plugin does allow for more complex ranking models to use, and we did expect that maybe this would actually decrease our performance. But we found that it actually improved things because we were doing a lot of recomputation of ranking signals using our previous method, and the Learning to Rank model could more efficiently reuse signals when we moved to it. There were also a bunch of more ideas that didn't work. So we tried using term vectors, which should, in theory, improve highlighting performance. We didn't observe that. We tried roaring bitmap filtering for some parts of our query. We didn't see that overly improved things. Now, it's worth pointing out that many of these ideas may work for your use cases. They just didn't work for our use cases. Query caching in particular was an interesting one for us, which we thought that we could tune the query cache and get better performance. But it turned out that because we have a lot of per user query query differences, we got a very low hit rate on our cache. So I think that this would be an area that we'd need to make more improvements into OpenSearch to be able to have finer grained control of what parts are cached and what parts are not. We also tried the boolean filter for ID lookups. This is ID lookups in an inverted index can be quite inefficient, and this is a technique that should improve it. We didn't observe those improvements for our use case, but it's certainly worth a look. It might improve things for yours. So the end result, we actually managed to get it down to about 200 milliseconds, stacking many of these improvements on top of each other. We're still in the process of rolling this out to production. Some changes, so you won't see this today in production, but hopefully soon you will. So closing thoughts. I've brought up the documentation quite a bit. It really is a great resource, particularly for performance tuning. So certainly make use of that when investigating ideas. Explore experimentally. We had plenty of ideas. We thought we were going to make some major improvements on, and they didn't turn out that way. And there were some areas that we were kind of lukewarm on, and we were surprised at the results that we got out. Finally, the latency in OpenSearch is improving by every release. Some of the features, for example, the use of concurrent segment search are actually enabled by default in OpenSearch 3.0, for example, and every new release does add more features, and so you may not realize that there are some new features you make use of for performance improvements. Thanks, everyone.
Hey, thank you, Zeshan. It was a really interesting talk. Should we open Q&A?
Yeah.
Yeah.
Any questions?
Hey, my question is regarding the parallelism using the multi-search which you were you were talking about, right? How did you achieve? How were you able to perform a split a single query into multiple queries? Or how did you achieve parallelism?
Yeah.
I wanted a bit.
Yeah. So is this still on? Yeah. Okay. So in our case, you can think of it as like we're performing the same search, right? So like the root of the query is still the same, right? We're doing some sort of keyword search, for example. But what we found was that to some extent it is redoing some work, right? But in one of our cases, we had a lot of kind of recency signals and personalization signals that were quite expensive, but were also constrained to a subset of the documents. And so when pulled out in isolation, they actually ran quite efficiently versus the remainder of our query, which was kind of searching a broader corpus of documents, which when we pulled that out, it could run quicker. So that's where we saw the improvement there.
how do you do the merging? Is it at the client end you merge the results and show the?
Yeah, so we have techniques that we use for merging the results together. You don't have to use multi-search. For example, you can use a hybrid search and in OpenSearch and make use of merge models that are integrated into OpenSearch, or use the arithmetic means and things like that merge results together.
Okay.
You mentioned that when you were trying to, the ideal case that you were sort of trying to emulate, like per index, like tenant level indexes. I understand the overhead there, but when you did like a per shard, like one tenant per shard, you mentioned that at 3,500 shards you sort of like found problems, but I just checked it again to ensure I'm right. I believe the default limit's around 1,000 or so. We're already exceeding that. So my question was, if we spread tenants across shards, we would have to search across all shards. And like searching over thousands of shards, I presume it would be like very bad.
Yeah, so we make use of routing rules to the you can use custom routing to.
So then you still have some sort of mapping for like one tenant still does not go to all shards.
Yes.
Oh, okay. Yeah, that makes sense.
Hi, so I have a question on the ingestion side of things. So if you have a cluster running serving query traffic for multiple tenants, you might have ingestion traffic on it as well. So did you find that impacted query traffic, latency, or bursts of those while you are operating the cluster?
Yeah, we've definitely seen this in the past. There's a lot of interesting things to protect you moving forward from that thing. We've explored admission control on ingestion. We've also, with 3.0, we're very interested in the contribution Uber made with the pool-based ingestion. And finally, in 3.0, there's the index and search segregation, which really allows you to avoid these scenarios that you're talking about.
Sure, got it. Thanks.
We'll take one last question.
Thank you. Nice talk. You mentioned about the shard level overhead, right? And you also measured it. Can you expand on it? How did you measure it?
Yeah. So the experiment was essentially start up an OpenSearch cluster and just create empty indexes or empty shards, and then attach your Java heap like a debugger, and like understand how much heap is getting used, and then watched it until we ran out of memory, and that gave us a good sense of like roughly how much memory overhead we were experiencing. Thanks everyone.
Folks. Thanks,
you can talk to me at the booth if you have more questions.